Let's derive the differential equation for a circuit with an inductor and a capacitor. And here, the capacitor is fully charged initially. But note that this charge had to come from somewhere. So we would have had some EMF source in the circuit, being a battery. And then we'd apply Kirchhoff's voltage law to the circuit with an EMF source. So we'd have a potential increase across the battery, a potential drop across the inductor, and a potential drop across the capacitor while it's being charged. And therefore, when we remove the battery, we get rid of this EMF source from Kirchhoff's voltage law. So this ensures we have a proper sign convention for a circuit with only passive components. So when we close this switch, the capacitor is fully charged, and this is a differential equation that describes the charge in the circuit. So noting that the current is the first derivative of charge with respect to time, and cancelling out the negative signs, we can write this differential equation as the inductance by the second derivative of charge with respect to time, plus the charge on the capacitance is equal to 0. And if we divide through by L, we get d2q dt squared plus 1 on LC by Q is equal to 0. And now we set the square of the frequency as 1 on LC. So we end up with the ODE d2q dt squared plus omega squared q is equal to 0. And recall that this is similar to the ODE for a harmonic oscillator, so we can use that solution directly, which we obtained from the mechanics part of the course. So the charge as a function of time is equal to the initial charge in the capacitor, which we'll call Q max, by cosine omega t. So note that at t equals 0, we have the charge in the capacitor being a maximum. And then to obtain a current as a function of time from this equation, we can differentiate the charge with respect to time. So what we get is minus omega Q max by sine omega t. So at time t equals 0, when we have the maximum charge in the capacitor, the inductor is preventing the capacitor from discharging at time 0. So therefore the current in the circuit at time 0 is 0. And if you differentiate this with respect to time again, we get minus omega squared Q max by cosine omega t. So at time t equals 0, the change in current is at a maximum, and therefore the back EMF provided by the inductor is at a maximum, which is preventing the capacitor from discharging. And next we'll plot this solution and observe the behavior of the circuit. Let's interpret the solution to our differential equation that describes the behavior of an LC circuit, where we had the angular frequency as the reciprocal of the square root of the inductance by the capacitance. And for simplicity, for this particular circuit, we've taken our inductance as 1 Henry and the capacitance as 1 farad. So I'll leave it for you as an exercise to determine the SI units, and you'll find that omega is in radians per second. And we'll derive the following solution, which is a charge as a function of time, and differentiating this gave the current as a function of time. So initially, the capacitor is charged. We will have negative charge on the bottom plate and positive charge on the top plate. And this red curve describes the charge on the top plate. And the green curve is the current as a function of time. So when this switch is closed, the inductor resists the flow of current initially, and then current begins to flow through the circuit in this direction. And here we're using the direction of conventional current. So as current flows to the inductor, the capacitor discharges. So at this point, there's no more charge on the top plate, and the magnetic field in the inductor has the maximum amount of energy. So remember, the energy stored in the inductor is 1/2 by the inductance by the square of the current. So at this point, the inductor is behaving like a wire. So current continues to flow through it, and the capacitor is getting charged at this stage. So the bottom plate will gain positive charge, which will push positive charge away from the top plate, so the top plate becomes negatively charged. And then when the capacitor reaches a maximum charge, the current drops to 0. So then the capacitor gets discharged, and the current changes sign. So effectively, now the current is flowing in the opposite direction. So when the capacitor gets fully discharged, the charge on the bottom plate will be 0, and the energy in the inductor is a maximum. So therefore the inductor behaves like a wire, and current continues to flow through it and charges up the top plate of the capacitor, which pushes positive charge away from the negative plate, so the bottom plate becomes negatively charged. So when the capacitor is fully charged, the magnetic field in the inductor has 0 energy. So there's no current flowing through the inductor. So this state is the same as this one. So we call this the period of the oscillation, or the time taken to complete one full cycle. So note that the frequency is the angular frequency on 2 pi. So this will be in hertz, or the reciprocal of second. And the period of the oscillation is the reciprocal of the frequency, which will give units of seconds. So in this case, given the inductance of 1 Henry and capacitance of 1 farad, the angular frequency is 1 radian per second, and therefore the frequency of the oscillation is 1 on 2 pi hertz, and therefore the period is the reciprocal of the frequency, which is 2 pi seconds. So in this case, it takes 2 pi seconds to complete one cycle. And note that in reality, there's resistance in the wire, so energy is going to be dissipated, and this oscillation will not continue on forever. Similar to the harmonic oscillator, For an LC circuit, we can determine the maximum current in the inductor using the conservation of energy within the circuit. So initially the capacitor was fully charged, and then we close this switch to get current flow within the circuit, and we derive this differential equation, which is similar to the harmonic oscillator, with the frequency being the reciprocal of the square root of the inductance by the capacitance. And we derive this solution for the charge as a function of time, and differentiating this, we got the current. So at a particular time, the total energy stored in the capacitor and inductor is equal to 1/2 by the capacitance by the voltage across the capacitor at time t squared, and plus 1/2 by the inductance by the current squared. And remember that the capacitance was equal to the charge on the voltage, so we can write the voltage as the charge on the capacitance. So here we get the charge as a function of time squared on the capacitance squared. So therefore we get 1/2 by Q squared on C. So we have 1 on 2C by the charge squared, so that would be Q max squared by cosine squared omega t, and plus 1/2 by the inductance by the square of the current, so that will be omega squared Q max squared by sine squared omega t. And now using the angular frequency, we can write omega squared as 1/LC. So the inductance cancels, and we obtain 1 on 2C by this expression. And now, if we factor out 1 on 2C by Q max squared, cosine squared omega t plus sine squared omega t is 1. So therefore at any time, the total energy stored in the capacitor and inductor is constant. So using the conservation of energy, we have the total energy stored in the LC circuit being equal to the energy stored in the capacitor at time t. So we have 1 on 2C by Q of t squared plus the energy stored in the inductor at time t. So if we want the maximum current in the inductor, we have the case where the capacitor is completely discharged. And we saw that in our solution. So for that case, Q at time t is 0, and cancelling out the half on both sides, we get Li max squared is 1 on C by Q max squared. Or the maximum current is equal to 1/root LC, which was the angular frequency, by Q max.